Our next speaker will be Aigerim Nurbayeva, a PhD student in robotics engineering at Nazarbayev University, Kazakhstan. Her current focus is on physical human-robot interaction, which is based on developing deep learning-based and model-based motion planning algorithm for industrial manipulators in the presence of human operators. Let's welcome Aigerim.
Hi everyone. Today I want to discuss the use of deep imitation learning techniques in physical human-robot interaction tasks. So as you can see from the image, physical human-robot interaction, or shortly PHRI, is a system where a human and a robot can work in the shared workspace. Sometimes they can have physical interact with each other. So manufacturers believe that by improving the physical human-robot interaction task, we can increase the efficiency, productivity, profitability of their activities. However, the main important aspect in PHRI is to ensure safety for humans, to prevent the accidents that could injure humans. One of the most widely used methods in the world is called speed and separation monitoring, or shortly SSM, in which the maximum allowable speed of the robot is calculated depending on the distance between human and the robot. If the human comes closer to the robot will automatically slow down or stops depending on the situation. So we wanted to use this speed and the separation monitoring in our task alongside with the model predictive controller. Model predictive controller works by solving numerical optimal control problem in finite time horizon, focusing on the providing only the first calculated value to the robot as a control inputs. So, however, this model predictive controller has one big drawback. It cannot be, actually it can be implemented in the real time. However, there might be some situations that when we use SSM alongside with the MPC, probably there is time limitations to implement the robot's trajectory in the real time. So that's the reason why we use deep imitation learning techniques to approximate nonlinear model predictive control solutions. Here I want to explain about deep imitation learning. Imitation learning is a type of machine learning process in which computer learns to imitate the behavior of the expert based on the experiments. So in our experiments, we use model predictive controller as an expert because it knows everything about the system. It knows how to control the robot. So computer based on the information about the system and the output from the nonlinear model predictive controller, it builds the data set. And the deep neural networks, or shortly DNNs, are trained based on that data set. After model is trained, it can be used to imitate the behavior of the nonlinear model predictive controller. However, this model is also have one drawback. As long as the model is trained using the solutions of the expert, there might be situations that not given during the examples. So the robot is not ready to solve unseen situations. So in order to overcome this general machine learning problem, Ross and the other authors introduced dataset aggregation algorithm, in which the problem can be solved using the, sometimes providing the current policy from the nonlinear model predictive control as an expert, sometimes from the deep neural networks. So here I can explain the information about the system and the information from the nonlinear model predictive controller can be stored in a data set, and the deep neural networks, based on that data set, it will train that data set and provide an action to the robot to control it in the real time. So probably we can solve this problem using providing real-time experiments. In our experiments, we used Andy dataset in order to obtain human information. So that using feed-forward neural networks, it is possible to implement our problem. So the input of feed-forward neural networks consists from 6 neurons for the robot joint positions and 42 neurons for the human positions. However, we thought that 42 neurons might be a lot, so we wanted to decrease that size of data using autoencoders here. Using the autoencoders, we could increase it until 24. Then, in the input here, we have like 30 neurons as 30 neurons, and 6 from the joint positions, and 24 from the human positions. And we ran the experiments. We trained it, and during the testing, we observed that sometimes this model doesn't satisfy SSM constraints. So in order to overcome this issue, we designed a safety filter, which is actually the one step of optimal control problem, which checks DNN outputs to SSM constraints. After checking this information, we can provide this information to the robot, and the robot and the human actually are in safe. So during the experiments, here we can observe the learning curve from our experiments. We can see that from very beginning, our loss value is really high. So this is the reason why during the deep imitation learning, actually the robot doesn't know anything about the environment. So it will make a lot of mistakes at the beginning, but time by time, and in our case for 2,000 episodes, this loss value is decreased, and it means like the robot is controllable in physical human-robot interaction task. In the below, we can see the results from 50 experiments with a walking human. And here we can see that our developed algorithm, the DACA-DNN, here it means like Dagger-based algorithm, outperforms a model-based model predictive controller for all parameters, including cost, task completion time, and computation time. So in the next slide, I want to show my video from the real-time experiments. So we tested the robot with nonlinear model predictive controller and the Dagger controller. Here we can see that the human is standing close to the robot, and the robot is able to avoid it. And we can see that the Dagger-based algorithm can finish the task faster than the model-based algorithm. So that's it from me. Thank you for your attention.